Welcome back to another blog. This is James Kelly. It's June 19th, 2017. This blog's called Are Service Meshes the Next Gen SDN? And you can always find my blogs first on jameskelly.net and follow me on LinkedIn. Away we go. Are service meshes the next gen SDN, software-defined networking? Whether you're adopting a containers or a functions as a service stack or both, in the new world of microservices architectures, one thing that's grown in importance is the network, because of three things. One, microservice application building blocks are decoupled from one another over the network. They reintegrate over the network with APIs as remote procedure calls, or RPC, that have evolved from the likes of Corba and RMI past web services with SOAP and REST to new methods like Apache Thrift and the even fresher gRPC. It's a new CNCF project donated by Google for secure and fast HTTP2 based RPC. So RPC's been around for a long time, but now the network is actually fast enough to handle it as a general means of communication between application components, allowing us to break down monoliths where service modules would have been previously bundled or coupled with tighter API communications. Based on package includes, libraries, and, well, some of us may even remember more esoteric IPC. The second point, 2. Each microservice building block scales out by instance replication. The front end of each microservice is thus a load balancer, which is itself a network component, but beyond that, the services need to discover their dependent services, which is generally done with DNS and service discovery. 3. To boost processing scale-out and engineer better reliability, each microservice instance is often itself decoupled from the application state and its storage. The state is saved over the network as well. For example, using an API into an object store, a database, a key value store, a streaming queue, a message queue, all of those things, they're APIs over the network. There's also the good old disk, but such disks and accompanying file systems too may be virtual network mounted volumes. The API and the RPC accessible variants of storing state are themselves systems that are microservices too, and probably the best example of the ones that use disks, in fact. And they would incorporate a lot of other distributed magic to make good on whatever promises that they make, and that magic is actually performed over the network too. So hopefully we're all on the same page now as to why the network is important, microservices glue. If this was familiar to you, then maybe you already know about cloud-native SDN solutions and service meshes too. The idea and implementation of a service mesh is fairly new. The topic is also garnering a lot of attention because they handle the main networking challenges listed above, and much more in the case of new projects like the CNCF Linkerd, and even more new and newly launched project, Istio. Since I've written about SDN for container stacks before, namely OpenContrail for Kubernetes and OpenShift, I'm not going to cover it super deeply, nor am I going to cover service meshes, at least not in general detail, but I will cover them when I make comparisons. I will also put in some references below and throughout, and I've tried to organize my thoughts from this long blog by compartmentalizing the comparisons so that you can skip the technical bits that you might not care for, I don't know, or just dive right into the ones that do strike you as interesting and matter most to you. So on to the fun. Let's look at some of the use cases and features of service meshes and compare them to SDN solutions, mostly OpenContrail, so we can answer the question posed in the title, Are service meshes the next generation of SDN? Section 1. automating SDN and service meshes. So first, let's have a look at 3 general aspects of automation in various contexts where SDN and service meshes are used. 1, 2, 3. 1, programmability. 2, configuration. And 3, installation. 1, programmability. When it comes to automating everything, programmability is a must. Good SDNs are untethered from the hardware side of networking, and many, like OpenContrail, offer a logically centralized control plane with an API. There's your programmability. The main 2 service meshes introduced above do this too, and they follow an architectural pattern that's similar to SDNs, of a centralized control plane with a distributed forwarding plane agent. While Istio has a centralized control plane and an API for it, Linkerd is more distributed in its nature, but it offers an API through its Namerd counterpart. Most people would probably say that the 2 service meshes gRPC API is more modern and advantageous than the OpenContrail RESTful API. But then again, OpenContrail's API is well built out and tested compared to Istio's, still primordial API functions. 2, configuration. A bigger difference than the API is in how functionality can be accessed. The service meshes take in YAML to declare configuration intent that can be delivered through a CLI. I suppose most people would agree that that's an advantage over SDNs that don't offer that, and at least OpenContrail doesn't today. In terms of a web-based interface, the service meshes do offer those too, and so do many SDNs. OpenContrail's web interface is fairly sophisticated after 5 years of development, yet still modern feeling and enterprise friendly. Looking towards network as code trends, however, CLI and YAML is codable and version controllable more easily than, say, scripting OpenContrail's API calls. In an OpenStack environment, well, there, OpenContrail can be configured with YAML-based heat templates, but that's less relevant, or even not relevant, in a container-based Kubernetes and OpenShift world. In a Kubernetes world, OpenContrail SDN configuration is annotated into Kubernetes objects. It's intentionally simple, so it's just exposing a fraction of the OpenContrail functionality. It remains to be seen what will be done with Kubernetes TPRs, config maps, or through some OpenContrail interpreter of its own. 3, installation. When it comes to getting going with Linkerd, having a company behind it, Buoyant, means anyone can get support. But getting it going day one looks pretty straightforward on one's own anyways. Deployed with Kubernetes in the model of a daemon set, it's straightforward to use out of the box, I'd say. Istio is brand new, but already has Helm charts to deploy it quickly with Kubernetes, thanks to our friends at Deis. Using Istio, on the other hand, means bundling the Envoy proxy, its Envoy proxy, into every Kubernetes pod as a sidecar. That's an extra step, and it looks fairly painless, but there's still that kube inject command. I guess it does the work for you. The sidecar versus daemon set considerations aside, this bundling kube inject is doing some magic, and it's important to understand what it's doing for debugging later. When it comes to SDNs, they're all different with respect to deployments. OpenContrail is working on a Juniper-supported Helm chart for simple deployment, but in the meantime, there are Ansible playbooks and other comparable configuration management solutions offered by the community. One thing OpenContrail has in common with the 2 service meshes is that it's deployed as containers. One difference is that OpenContrail's forwarding agent on each node is both a user space component and a kernel module, or a DPDK-based module or SmartNIC-based module. They're containerized, but the kernel module is really only there for installation purposes, to bootstrap the insmod installation. Now you may feel ambivalent towards kernel modules. The kernel module will obviously streamline performance and integration with the networking stack, but the resources it uses are not container-based and thus resource restricted. They're not. So resource management is different than, say, a user space sidecar process. Anyways, this is the same deal as using kubeproxy or any IP tables-based networking, which the OpenContrail vRouter replaces. Section 2. SDN and Service Meshes, Considerations in Devops. When reflecting on microservices architectures, we've got to remember that the complexity does not stop there. There's also the DevOps apparatus to manage the application through dev test staging and prod and through continuous integration, delivery, and response. So let's look at some of the considerations. First up, number 1, multi-tenancy / multi-environment. In a shared cluster, code shouldn't focus on operational contexts, like operator or application dev test environments. To achieve this, we need isolation mechanisms. Kubernetes namespaces and RBAC help with this, but there's still more to do. I will quickly recap my understanding of the routing in OpenContrail and the service meshes to better dissect the considerations for context isolation. OpenTag for background. OpenContrail for Kubernetes recap. One common SDN approach to isolation is overlay networks. That's right. They allow us to create virtual networks that are separate from each other on the wire, as in different encapsulation markings, and often in the forwarding agent as well. And this is indeed the case with OpenContrail. But OpenContrail also allows higher level namespace like wrappers called domains / tenants and projects. Domains are isolated from each other. Projects within domains are in turn isolated from each other, and virtual networks within projects are also isolated from each other. This hierarchy maps nicely to isolate tenants and the dev test staging prod environments, and then we can use a virtual network to isolate every microservice. To connect networks, optionally across domains and projects, a policy is created and applied to the networks that need connecting. And this policy can optionally even specify direction, network names, ports, service chains to insert, for example, a stateful firewall service. So the way that these domains, projects, and networks in OpenContrail are created for Kubernetes is based on annotations. OpenContrail maps namespaces to their own OpenContrail project or their own virtual network, so that optionally all microservices are going to be reachable on one big network, similar to the default cluster behavior. There are security concerns there. And OpenContrail can also enforce ACL rules and automate their creation as a method of isolating microservices for security based on the Kubernetes object annotations, or by implementing the Kubernetes network policy objects as OpenContrail security groups and rules. Another kind of new annotations on objects like the Kubernetes deployments, jobs, or services would specify the whole OpenContrail path, as in domain, project, and virtual network of choice. Personally, I think the best approach is a hierarchy designed to match the DevOps teams and environment structure that makes use of the OpenContrail model of segmentation by domain, project, and network. And this is unfortunately perhaps in contrast to the simpler yet more frequently used global default deny rule and the ever-growing whitelist that ensues that basically turns your cluster into Swiss cheese. Have fun managing that. The overlay for SDN is at layer 2, 3, and 4, meaning that when the packet is received on the node, the vRouter, in OpenContrail's case, will receive the packet destined to it and look at the inner header. aka the VXLAN ID or the MPLS LSP number, to determine the domain/tenant, the project, and the network. Basically, the number identifies which routing table will be used as a lookup context for the inner destination address, and then, pending any ACLs, the packet's handed off to the right container or pod interface, per the CNI standards. There's your OpenContrail and Kubernetes background. Now for some service mesh background. The model of Istio's Envoy and Linkerd, at least insofar as they're used, which can be on a per microservice basis, is that there is a layer 7 router and proxy in front of your microservices. All traffic is intercepted at this proxy and tunneled between nodes. Basically, it's an overlay at a higher level. The overlay at layer 7 is conceptually the same as SDN overlays, except that the overlay protocol over the wire is HTTP or HTTP2 or TLS with one of those. In the daemon set deployment mode of Linkerd, there's one IP address for the host, and Linkerd will proxy all the traffic from all the pods. It's conceptually similar to the vRouter, except in reality it's just handling HTTP traffic on certain ports as opposed to all traffic. Traffic is actually routed and destinations are resolved in the Linkerd setup using a delegation tables format, or DTABs for short, which is inherited from the Finagle project. In the sidecar deployment model for Linkerd, or for Istio's Envoy, which is always a sidecar, the proxy is actually in the same container network context or CNI context as each microservice because it's in the pod, it's a sidecar. There are some IP table tricks that they do there to sit in between your application and the network. In Istio, the pilot component or control plane, and Envoy, the distributed data plane component, traffic routing and destination resolution is primarily based on the Kubernetes service name. And that brings a close to our background tag. With that background, here are finally a few implications for multi-tenancy, the topic that we started off on, as it relates to considerations for DevOps. Let's observe that in the SDN setup, the tenant, the environment, and the application or network, the classification happens in the kernel vRouter. In service mesh proxies, we still need a CNI solution to actually get the packets into the pod in the first place. In Linkerd, we need DTAB routing rules that include tenant, environment, and service, and DTABs seem to give a good way to break this down that's manageable. In the sidecar mode, which is a little bit more frequently used for Envoy, let's say, it's likely that the pod in which traffic ends up already has a Kubernetes namespace associated with it, and so we just map a tenant or environment outside of the Istio rules and focus on resolving the service name to a container and port when it comes to Envoy. It seems that OpenContrail here has a very good way to match the hierarchy of separate teams and separate out those RBAC and routing contexts. Linkerd with DTABs are probably a more flexible way to create as many layers of routing interpretation as you want, I suppose, but it may need a stronger RBAC to allow splitting of the DTABs among team tenants for security and for coordination. Istio, well, it doesn't really do much in the way of isolating tenants and environments at all, but I think that's just because it's out of scope for it, which seems reasonable, since Envoy is always a sidecar container, and you should basically have the underlying multi-tenant networking context anyways, once you get traffic into the sidecar, into the pod, basically. One final point is that service discovery is baked in to service mesh solutions. But it's still important in the SDN world, and systems that include DNS, like OpenContrail does, can help manage name resolution in a multi-tenant way, as well as provide IP address management, or IPAM for short, where you can bring your own IPs and have them overlapping between different subnets of different virtual networks, of different projects, of different domains, however you like, across all of those environments, however you want to carve it up. Now, obviously, IPAM is out of scope for service meshes, but with respect to multiple teams and the dev test staging prod environments, it could be desirable and useful to have the same IP address management pools and subnets across those environments. 2. Deployment and load balancing. When it comes to deployment and continuous delivery, the fact that SDN is programmable helps, but service meshes have a clear advantage here because they're designed with CD in mind. To do a blue-green deployment, for example, with SDN, it helps to have a floating IP functionality. Basically, we can cut over to green, let's say, which means we float a virtual IP address to the new version of the microservice. And we can safely float it back over to the blue deployment if we need to in case of an issue in the green deployment. As you continuously deliver or promote staging into the non-live, whichever color that is, deployment, you could still reach it with a different floating IP address. OpenContrail handles overlapping floating IPs, so you can juggle this however you want to. Service mesh routing rules, well, they can achieve the same thing, but based on routing switchovers at the HTTP level that point to, for example, a newer backend version. What service meshes further allow is also traffic rollover, like in this example, see the link, showing a small percentage of traffic at first and then forwarding all of it, effectively giving you a canary deployment that is traffic load oriented as opposed to a Kubernetes rolling upgrade or the Kubernetes deployment canary strategy that gives you a canary but that's instance count based, not traffic load oriented. And the instant count based version relies on load balancing across instances to partition traffic. This brings us to load balancing, of course. Well, balancing traffic between the instances of a microservice, by default in Kubernetes, it happens with the kube proxy and its controller by programming IP tables. Now, in OpenContrail, we've seen before, there are a bit of performance and scale advantages of using OpenContrail's vRouter, which uses its own ECMP load balancing and NAT instead of the kernel's IP tables. Service meshes also handle load balancing, of course. You probably have heard. They support wider ranging features, I'd say, both in terms of load balancing schemes like EWMA, exponentially weighted moving average, and also in terms of cases to eject an instance from the load balancing pool, like if they're slow. Of course, service meshes do also handle load balancing for ingress, HTTP front-ending in other words. Linkerd and Istio integrate with the Kubernetes ingress as ingress controllers. Now, while most SDNs don't seem to offer this, OpenContrail does. It does have a solution here that's based on HA proxy, an open source TCP proxy project. One difference, however, is that OpenContrail does not yet support SSL or TLS, but there are also Kubernetes pluggable alternatives like Nginx for pure software-defined load balancing. 3. Reliability engineering. Yes, I categorize SRE and continuous response under the Devops umbrella. In this area, since service meshes are more application aware, well, I guess it's no surprise that they do the most to further the causes of reliability. When it comes to reliably optimizing and engineering performance, one point here from above is that EWMA, the exponentially weighted moving average, and such advanced load balancing policies will assist in avoiding or even ejecting slow instances, thus improving the tail latency of applications. A Buoyant article in a blog about performance addresses the performance in terms of latency directly. Envoy and Linkerd are, after all, TCP proxies, and unpacking and repacking a TCP stream is seen as notoriously slow if you're in the networking world. I can attest to this personally, recalling one project I assisted with that did HTTP header injection for ad placement purposes. Anyway, CPUs have come far, and Envoy and Linkerd are probably some of the fastest TCP proxies that you can get. That said, there are always sensitive folks that balk at inserting such latency. I thought it was enlightening, though, that in the test conducted in the article cited above, they've actually added more latency and more steps in adding Linkerd, but because they're also adding more intelligence in the load balancing, they netted an overall latency speed up. Pretty cool. The consensus seems to be that service meshes solve more problems than they can create, and one of those would be latency. So are they right for your particular use case? Well, as somebody highly quoted once said, it depends. As is the case with deep packet inspection or DPI-based firewalls, these kind of traffic processing applications with TCP proxies can have great latency and throughput for a given feature set or a given load, but then wildly different performance by turning on certain features or under load. Not that it's a fair comparison, but the lightweight stateless processing that an SDN forwarding agent does is always going to be faster than such proxies, especially when, like for OpenContrail, there are smart NIC vendors implementing the vRouter in hardware. Another area that needs more attention and discussion, I suppose, in terms of reliability engineering is security. As soon as I think of a TCP proxy, my mind wanders about protecting against a DOS attack, because so much state is created to track each TCP session, plus HTTP, plus all of the extras that these applications, service meshes, in other words, are doing. A nice way, however, that a service mesh just really brilliantly solves this is through the use of TLS, actually. While Linkerd can support this, Istio makes it even easier because of this control plane component called Istio Auth for certificate and key management. This is a great step, not only securing traffic over the wire, which SDNs could do too with IPsec, etc., but also the service meshes employing this are making strong identity-based AAA for each microservice possible. It's worth noting that these proxies can actually change the wire protocol to anything that they can configure too, regardless of if it was initiated as such from the application. So, just as an example, an HTTP request that was initiated by the application could be sent as HTTP2 within TLS on the wire. I'll cap off this section by mentioning circuit breaking. I don't know of any means that an SDN solution could do this very well without interpreting a lot of analytics and application tracing information, and then feeding that back into the API of the SDN. It sounds complicated. Even if that is possible in theory, service meshes already do this today as a built-in feature to gracefully handle failures instead of having them escalate. Four, testing and debugging. Well, this is an important topic, but there's not really an apples to apples comparison of features. So I'll just hit the prominent points on this topic separately. Service meshes. Well, service meshes provide an application RPC-oriented view into the intercommunication, the mesh of microservices. This information can be super useful for monitoring and ops visibility, and during debugging by tracing the communication path across an application's set of tiers or microservices. Linkerd does this by integrating with Zipkin for tracing and other tools for metrics, and works for applications that are written in any language, of course, unlike some language-specific tracing libraries. Service meshes also provide per request routing based on things like HTTP headers that can be manipulated and injected for some pretty clever testing. Additionally, Istio also provides fault injection to simulate blunders in the application, saving them hopefully from happening in production. On the SDN side of things, solutions differ. OpenContrail is fairly mature in this space compared to other choices one has with CNI providers. OpenContrail has the ability to run packet capture and sniffers like Wireshark on demand, and its comprehensive analytics engine and visibility tools expose flow records and other traffic statistics. Aside from debugging, at more of a network level obviously here, there are interesting security applications for auditing the ACL deny logs. Finally, OpenContrail can tell you the end-to-end path of your traffic if it's run atop of a physical network instead of a cloud. All of this can potentially help debugging, but the kind of information is probably far more indirect vis-a-vis the application, and thus is probably better suited for NetOps. Section 4. Legacy and other interconnection. Service meshes seem great in many ways, but one hitch to watch out for is how they can allow or block your microservices connecting to your legacy services, or any services for that matter that don't have a proxy in front of them. Some examples. If you're storing state in S3, or making a call to a cloud service, that's an external call. If you're reaching back to a legacy application like an Oracle database, same deal, it's outside of the service mesh. If you're calling an RPC of another microservice that's not on the service mesh, because maybe, I don't know, for example, it's sitting on a virtual machine instead of a container, well, same again. If your microservice is supposed to deal with traffic that isn't TCP traffic, well, that too isn't going to be handled through your service mesh. For example, DNS, not TCP, it's UDP. Ping is ICMP. In the case of Istio, you can set up egress connectivity with a service alias, but that may require changes to the application, so a direct pass-through is perhaps a simpler option. Also, there are a lot of variants of TCP traffic that are not HTTP, nor directly supported as higher level protocols riding on HTTP, in terms of support within these proxies, I mean. So some common examples, SSH and mail protocols. There's also the question of how service meshes will handle multiple IPs per pod and multiple network interfaces per pod once CNI soon allows it. So you most certainly have some of this communication in your applications that doesn't quite fit into the mesh. In these cases, you not only need to plan how to allow this communication, but also how to do it securely, probably with an underlying SDN solution like OpenContrail that can span Kubernetes as well as OpenStack, VMware, and bare metal. Section 4. What do you think? Going back to the original question in the title, are service meshes the next generation of SDN? On one hand, yes, because they're eating a lot of value that some SDNs provided by enabling microsegmentation and security for RPC between microservices. Service meshes are able to do this, but with improved TLS-based security and identity assignment to each microservice. Also, as we said, service meshes are adding advanced application-aware load balancing and fault handling that's otherwise really hard to achieve without application analytics and code refactoring. On the other hand, no, because service meshes sit atop of CNI and container connectivity. They ride on top of SDN, so they'll need a solid foundation underneath them. Moreover, most teams will probably want multiple layers of security isolation when they can get microsegmentation and multi-tenancy that comes with SDN solutions like OpenContrail without any performance penalty. SDN solutions can also span connectivity across clusters, stacks, and runtimes other than containers, and of course satisfy the latency obsessed as we talked about. Either way, service meshes are a new, cool, shiny networking toy. They offer a lot of value beyond the networking and security values that they subsume, and I think we'll soon see them in just about every microservices architecture and stack. Section 5, more questions. Hopefully something in this never-ending blog makes you question SDN or the service meshes. Share your thoughts or questions. The anti-pattern of technology forecasting is thinking that we're done. So, some open questions to spark your creativity and juices. 1. Should we mash up service meshes and fit Linkerd into the Istio framework as an alternative to Envoy? And if so, why? 2. Should we mash up OpenContrail and service meshes, and how? And finally, the section on resources about learning about service meshes. 1, there's a link to the Istio blog. 2, there's a link to the Buoyant blog. 3, there's a link to the demo videos playlist put together by Lockie, who's awesome in demoing Istio with Kubernetes. Next, we have a link to Scaling Twitter. It's a podcast about Linkerd on Software Engineering Daily. Next, we have Service Proxying, a podcast about Envoy, also on Software Engineering Daily. And finally, Comparing Envoy and Linkerd, a link to the GitHub site of Envoy. It gives you their impression of Envoy versus Linkerd. I hope you enjoyed this blog. I enjoyed having you tuned in with me. Together is a great place to be. I hope you'll join me again. Thank you very much.